Good morning students. Today's topic is Davission and germer's experiment. So Davission and germers, they conducted experiment on electron diffraction pattern. The first experimental evidence of matter waves was given by these two American physicists, Davission and germer. They conducted the experiment in 1927. They not only give the experimental evidence of matter waves, and also they succeeded in measuring the wavelength of matter waves. Now, when they are doing the experiment on electron diffraction or the experiment reflection of electrons, the reflection became anomalous. So they suspected that electrons are behaving wave nature by diffraction, by forming diffraction pattern. Okay, so now discuss about the experimental arrangement of the Davission-Germer's experiment. It is a tungsten filament. It is made up of tungsten. It is heated to dull red color. It is heated up to dull red color. By heating, electrons are emitted due to thermionic emission. The electrons are emitted due to thermionic emission. Electrons are emitted due to thermionic emission. The emitted electrons are collimated by using slits. Here, two slits are placed by using slits S1 and S2. The electron beam is made into a narrow beam. This is made into fine pencil of electronic beam. The electrons, or the beam of electrons, is accelerated by giving voltage, by giving suitable voltage. So it is connected to the high tension battery. So voltage is applied by this battery, high tension battery. The positive terminal of the battery is connected to this apparatus. So by giving certain voltage, the electrons are accelerated, and the electrons are directed towards the nickel crystal. Here the nickel crystal is placed. It is a large single nickel crystal. So this nickel crystal acts as plane diffraction grating. It is act as plane diffraction grating. Okay, this is the nickel crystal. Nickel crystal acts as the target T. This is the filament F. tungsten filament. Now, after striking the nickel target, the electrons are diffracted in different directions. Here, the circular graduated scale is arranged. Circular graduated scale is arranged. On the scale, angles are graduated 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70, 80 and 90 and so on, like that. Here, the electrons are diffracted in different directions. So, this is the diffracted electrons. Here, a circular graduated, here a Faraday cylinder is placed. The Faraday cylinder consists of two walls which are insulated from each other. This Faraday cylinder is connected to the galvanometer. So galvanometer measures the intensity of diffracted electrons. The galvanometer measures the intensity of diffracted electrons. This is galvanometer. Now once again, look at the schematic diagram of Davission's and germer's experiment. They conducted the experiment on electron diffraction pattern. So here the diffraction pattern is formed by using nickel crystal. This apparatus consists of mainly three parts. One is electron gun, and the second one is nickel crystal target, and the third one is Faraday cylinder. Okay. Electron gun consists of a tungsten filament. This tungsten filament is heated to dull red color, up to dull red color, so that the electrons are emitted. The electrons are accelerated by giving certain voltage. By giving voltage, the speed of electrons increases. By giving higher voltages, the speed of electrons increases. The electronic beam is made into a narrow beam, into a like a fine pencil beam, by using two slits, S1 and S2. This narrow beam of electrons is directed towards the nickel crystal and strikes the nickel crystal. Here nickel crystal acts as the target. After striking, they are diffracted in different directions. They diffracted in all possible directions. That is, the diffraction pattern is formed. Here, the Faraday cylinder is placed. It can move on the circular graduated scale. Circular graduated scale. It can move from 29 degrees or 20 degrees to up to 90 degrees. Okay, now. So now, this is about experimental arrangement. Now let us learn the procedure, how this experiment is conducting. Let us learn the procedure. Here, angular distribution of electrons is measured by the electron detector at different voltages. For example, at 40 volts, 44 volts, 48 volts, and go on increasing at different voltages, the angular distribution is measured. Angular distribution means the angle made between incident ray and the reflected ray or the diffracted ray. Here the angle theta. Angular distribution means for example, theta is 10 degrees or 20 degrees, 30 degrees. At what angle the maximum intensity is noted or observed. So angular distribution is measured by the Faraday cylinder. Here the Faraday cylinder detects the electrons. When these electrons enter into the Faraday cylinder, ionization current is produced in the cylinder. The ionization current is measured by the galvanometer, which is connected to the Faraday cylinder. Okay, so the observations are repeated for different potentials. For example, take 40 volts, the values are noted. Deflecting angle, and current, I values. For different deflecting angles, different current values are noted. For example, deflecting angle is 10 degrees, 20 degrees, 30 degrees, up to 80 or 90 degrees. Different current values also noted by measuring with the galvanometer. Okay, so by taking the readings on the table, a graph is plotted between the current values and the angle between incident beam and the diffracted beam. So different angles. So this is the incident beam. This is the direction of the diffracted beam. The angle made between these two, and for example, it is conducted, the experiment is conducted at 44 volts. The graph is drawn like this. At 44 volts, 10 degrees, 20 degrees, 30 degrees, 40 degrees, at different angles, the current values are noted on the graph and points are joined. Then the graph is like this. And this experiment is repeated for 48 volts. Let us suppose the graph is, this is the incident beam, the angle between incident beam and diffracted beam, theta. It is conducted at 48 volts. This graph is like this. This graph is like this. And if it is conducted at 50 volts, and 50 degrees, the graph is like this. 54 volts and 50 degrees, the graph is like this. And as we increasing the potentials, 60 volts, the experiment is conducted for different angles, and the graph is drawn like this. Here we are observing different graphs. These graphs are plotted at different voltages. Every graph is drawn between the angle and the current values. This is the radial graph. So when we observe these four graphs, the curve is maximum at 54 volts and the angle is at 50 degrees. The curve is like this. The curve at the bump begins at 44 volts, and as we go on increasing the potential 48 volts, 54 volts, the bump begins maximum at 54 volts and at angle is 50 degrees. And as we go on increasing the voltage at 60 volts, the bump gradually disappears. That means the curve gradually disappears. So we observed different graphs at different voltages. So at 54 volts and at 50 degrees, the bump becomes maximum. At this value, it verifies the existence of electron waves. De Broglie is given a wavelength for matter waves. According to De Broglie, the wavelength of electrons associated with waves, lambda is equal to h by square root of 2mEV. Here h is the Planck's constant, m is the mass of the electron, E is the charge, here V is the applied voltage. By substituting these values, the value obtained is 12.26 by square root of V angstroms. So here in the experiment, we plotted different graphs. At maximum bump appears at 54 volts. It verifies the existence of the waves, electron waves. So here, applying 54 volts in this equation, 12.26 by square root of 54 angstroms. This is equal to 1.67 angstroms. This is equal to 1.67 angstroms. This is the wavelength obtained by De Broglie's wavelength theoretically, and the value is obtained from experiment. This is confirmed by the X-ray analysis. You know the X-ray analysis, the nickel crystal acts as the plane diffraction grating. Thus it has a space between two lattice points D is equal to 0.91 angstroms. 0.91 angstroms. You know Bragg's formula, 2d sin theta is equal to n lambda. Here n is equal to 1. First Bragg's plane, 2d sin theta is equal to lambda. Theta is the Bragg's angle. In this experiment, at theta is equal to 50 degrees, we got maximum bumping. So the corresponding angle of Bragg's plane is here. Consider a crystal. It has different planes. This is divided into different planes. The angle on the straight line is 180 degrees. From the experiment, we have theta is 50 degrees. It is theta dash and it is also theta dash. Theta dash plus 50 degrees is 2 theta dash plus 50 degrees is equal to 180 degrees. From this, theta dash is equal to 180 minus 50, 130, and theta dash is equal to 65 degrees. The angle 50 degrees is from experiment, and theta dash is corresponding angle of Bragg's family. The theta dash is 65 degrees, D is 0.91 angstroms. Lambda, we can calculate the lambda by substituting these values. 2 into 0.91 into sine 65 degrees. Sine 65 degrees. By simplifying these, we can get the lambda is equal to 1.65 angstroms. Now compare the values obtained from de Broglie's wavelength and from X-ray analysis. Here we are using same nickel crystal. Crystal is same. So by comparing these two values, 1.67 angstroms and 1.65 angstroms, these two values are same. Approximately these two values are in good agreement. That means electrons are the material particles. They exhibiting diffraction pattern. That means they exhibiting wave nature. When material particles exhibits wave nature, that is nothing but matter waves. According to de Broglie, matter waves are the moving particle is associated with a wave, is known as matter waves. So here in particles are electrons. The electrons are exhibiting wave nature. They are not moving in a straight line. When they are deflected, they exhibiting wave nature. That means they are not reflected in the same line. All the electrons are deflected at same angle. They are deflecting in this experiment at different angles, and the angular distribution also different. So from this, the diffraction pattern is exhibiting, so that the electrons are, you can say the electrons are exhibiting exhibiting wave nature. That means that is the matter waves. From this we conclude the Davission and germer, they conclude that material particles exhibiting wave nature, that means matter waves are exists, and also they succeeded in measuring the wavelength 1.67 angstroms. Okay, thanks to everyone.